All right, good morning, ladies and gentlemen. Our last final review is on kinematics. Do this now, scan the organization of the AP Physics equation sheet and examine each equation. And you will see how they are familiar to you, but maybe set up in a different way. And you want to be familiar with how they have them written here and understand how that relates to what you've been working with all year.
What's on the other side?
Now on this side, we've got constants.
This stuff is important too.
Symbols, units, helpful trig stuff. Okay.
You want to be familiar with it. You are familiar with it, should be familiar with it already.
Yeah.
But you don't want any surprises. You want to be as efficient as possible on test day.
Yes. Vector quantities have both magnitude and direction. Scalar quantities have magnitude only. Simple definition here. Vectors are graphically represented with arrows.
Yep.
In a vector diagram, a vector arrow may be moved around, but its length and direction must stay fixed.
Yep.
Vectors can be added together by placing the tail of one vector at the head of the other. The result of this addition is an arrow drawn from the tail of the first arrow to the head of the other to the last, and it's our resultant.
Could you show an example of that?
Yeah, so say we have this guy right here and this guy right here, and our resultant is going to be drawn like this.
Arrows are added head to tail.
And if you have something that looks like this, we could take this and move it over here.
Yeah, that's a free body diagram.
And we can move it that way.
That's right.
Right? Okay, so in this course, we will only be encountering 90-degree vector triangles like such. 90 degree. Okay, this allows you to use Thag's theorem, SOHCAHTOA, to find the magnitude and the direction of the resultant. Your best friend, SOHCAHTOA. Okay, so the field due.
Let's just make this drawing here.
So it says the field due to one charge is 5 newtons. And
pointing north. What direction is that? That's up. Okay. So you want 5 newtons up, 5 newtons north. And then 3 newtons per coulomb pointing west. The west is to the left, isn't it?
This way, right? So like this.
So there's your free body diagram. That's your free body. That is not vector addition. Vectors are added head to tail. So how would you make that vector addition?
Let's move that up here. So 3 newtons west. Okay, and what does it want to know?
What's the net field?
Figure that out.
So use Thag's theorem, square root of 3 squared plus 5 squared, square root. And then you have to use, I think you'd use the tangent function to find the angle, and the angle would be there.
Now, a couple of things about this angle. As you guys know, which one are you going to use? Are you going to use this angle? If you're going to use this angle right here, it needs to be, you know, to the left of the north or above the horizontal.
Say it relative to a reference frame.
Yeah, there's lots of different options you could do here. So what are you gonna do?
Yeah.
And make sure I think that might be the next slide. Okay, well it's coming up here. Okay, any resultant vector can be resolved into 2 perpendicular components if we know the length and direction of the vector arrow.
Yeah, so there's vector addition and then there's resolving single vectors.
So choose an appropriate reference frame for your perpendicular components, horizontal, vertical, north, south, east, and west.
Yep.
Do you want to draw out?
Well, we've got an example right
coming up here. Using your knowledge of triangle parts, the resultant is the hypotenuse, and components are adjacent and the opposite sides.
Yeah.
So,
well, now hold on a second because we've got an example.
Oh, we do. Okay, you've got a better memory than I do. Oh, there we are. Okay. Rope is pulled with 100 newtons of force at an angle of
38 degrees
above the horizontal.
So there's our single vector, and it's newtons.
Yes. Oh, sorry.
So what are the vertical and horizontal and vertical components?
We want to know what is this one and what is this one.
Got to know your triangle parts.
And yeah, go ahead, Boykin.
That green one, the horizontal is what part?
The adjacent.
It's adjacent to the angle, and the blue one, the vertical, is the opposite. So
this is going to be, if we wanted to figure out the force of this one, it's going to be the hypotenuse times the cosine of the angle, right? Which is 38. And then this one, f of y would be the
sine,
hypotenuse times the sine of the angle.
Yep.
Okay. Now, if you do not know how I'm getting those equations, you need to go back and rewatch the video originally for those. Okay. You're gonna watch it and be like, "Whoa, that makes so much sense." Okay. The change in position is called the displacement.
You go from that place to this place, and the distance is the displacement.
Yeah. Okay, the displacement is the shortest straight line distance between 2 points in a specific direction.
Yeah. It has magnitude and direction. It's a vector.
The ratio of the displacement to time required is called the average velocity.
How far you went divided by how much time is velocity.
Okay. The average...
Now go back to that for just a moment.
Right.
This is different from speed. Speed is distance over time. Speed is what the speedometer in your car tells you. It doesn't tell you what direction, and the direction could be changing. Displacement is the shortest straight line between 2 points divided by the time. So this is velocity is a vector.
Different than speed in that specific way that Boykin just talked about.
Yep.
Okay, average acceleration
Is the rate of change of velocity.
Now let's talk about these initial and final velocities over here. Oh, not yet. Okay. Oh, I think it's coming up actually.
All right.
So we'll hang on to
We'll
that.
get to that.
But we'll keep this in mind. So here's our average acceleration. You know this. You should have this written down somewhere. If you don't have it written down, write it down, because for our next trick, how is this the same?
And this is, notice that it doesn't say, this is V original, but this doesn't have a subscript. That's V final.
Yeah, so it seems like we're solving for V final, right?
Yeah, so go back to the previous slide.
So if we solve for V final here, we would multiply T, so now we get A times T, and then we would add initial velocity.
So V original plus AT.
And that's what we have here. Now, this is one of our kinematics, and you can see where it's derived from.
Yep.
Only instantaneous velocities are used in calculating acceleration.
Yeah, don't be doing speed as distance over time. Don't be doing that. It's the instantaneous velocity is at the end and at the start.
Yeah, so going back over here, that means that these are the instantaneous velocities at the start and the finish.
A moment in time.
And if you guys remember the roll the ball down the ramp lab that we did,
yeah,
and we calculated the acceleration on the ramp using this, the speed, the final speed from here
on the table,
and 0 for the top.
Yeah.
Okay. Okay. I think we just said this.
We did this.
Okay. Velocity may change either its magnitude, speed up or slow down, or direction.
Yep, so if it speeds up or slows down, that's an acceleration. If it turns, that's an acceleration as well, as we saw with things that go around a circle.
Okay, you can feel it when you experience an acceleration because of your inertia, because your mass, right?
That's right.
Okay. If you jump into the water from a diving board, will it take more or less time to hit the water if you run off rather than you just step off?
Yep.
Okay. How do we answer this question? Motion in 2 dimensions. The acceleration due to gravity is a constant near Earth's surface, ignoring air resistance. Thank goodness. Okay. So gravity pulls down, so G is always down.
Yep.
Okay. So gravity is always pulling down, G is always down. If an object's motion has both vertical and horizontal components, they are independent of each other. That is, the motion in one direction is unaffected by the motion in the other, as if the other didn't exist. So, to answer our question, it's coming up here soon. So the horizontal motion is constant. There is no acceleration here. So if I ever want to know the horizontal velocity, you always just use this equation right here.
Yeah, it stays constant.
Always, always, always. Okay? Now, the vertical motion accelerates and obeys all of the kinematic equations. So anything in the vertical component, that's where we're using those kinematics using G.
Yeah.
Do not use velocity equals distance over time in the vertical because it is for constant velocity.
You will burn in hell.
And we don't have constant velocity in the vertical direction.
Yeah.
So the time to reach the the water from a diving board is not affected by whether or not you run.
No, it's just how high up in the air you are.
Gravity's pulling down the same no matter what.
Yep.
Okay. And here is our lovely kinematics helper sheet here. And so here's our 4 equations. And what we do here is whichever variable is not present, whichever one we don't have here, we're going to put an X right there. So no acceleration, X. No distance, this one, X. No final velocity x, no time here x.
And so you come into a problem, you write down all this information that you're given, and there are 5 equations, five variables, and whichever variable is missing, that allows you to select which equation is appropriate.
Yep.
Now, sometimes they won't tell you the acceleration if it's falling. You'll have to just assume that acceleration due to gravity. Or they'll say, starting from rest, they won't tell you that the original velocity is 0. They'll say starting from rest, or slides to a stop, and the final velocity would be 0.
Or if you're throwing something in the air.
Yeah.
Okay. So these are the equations that we have been working with all year. But of course, when you guys are taking your tests, you're using your AP equation sheet, and this is what you're seeing.
Yeah, these are the only 2 kinematic equations that are going to be on the sheet.
Yeah, and well, actually, they give you this one too. I just realized up top there too.
Okay,
Yeah.
the original plus AT.
But they don't give
But notice they don't use final. They don't use a subscript for final.
Yeah, and also we're used to seeing Watt with this year, and so if you guys remember, we did an AP for response question at the beginning of the year that required us to subtract to do some math here with the
right, so x minus x original is a displacement. So D is equal to Watt plus 1/2 AT
And so
squared.
that's what we see right here. We just aren't used to seeing that extra initial displacement there. But it's all the same thing, and same with this. There's some extra fancy stuff there. Okay, and that's it. Okay, so go ahead and so at this point, I'm assuming that you've been going through the AP practice questions, and you are seeing, how to apply what you've seen in the videos here, and how to use this AP equation sheet on the practice questions. So keep going. One more set of practice questions, and then we're ready for the test.
Buena suerte.